All right, let's continue with this titration of a weak acid and a strong base. Here's where it's going to get fun. Just like all the other titrations, the first thing we want to do is recalculate the molarities of the acid and the base. Let's do the acid. The acid was originally 0.1 molar, which I think they stated earlier in the problem. Initially, we have 25 milliliters. We want to know the new molarity when we join these two solutions, when we combine volumes. So I should have a total volume now of 48.5 milliliters. M2, we plug it in our calculator. 0.0515-ish. Let's go 3 sig figs. We'll do the base, same way. Originally, the base, I get it, it's 4 sig figs, but we're usually good plus or minus 1. So I'm feeling more comfortable with 3. 6, 3. These volumes are in 3 sig figs. Whoopsie, 23.5 is the original volume of base. We want to know the new molarity at 48.5. M2. Ooh, perfect. 0.0515. Hey, this looks good. And again, it kind of reminds me of that last strong acid, strong base problem. We have the exact same molarities. So let's set up the ice table. We've got the acetic acid, which we will not dissociate because it's a weak acid. COOH. But we can dissociate the strong base. The sodium's a spectator, so we really only need to include the hydroxide. Hydroxide will attract the hydrogen, so we'll be left with the acetate ion. COO negative. And we'll form some water. Ice table, ICE. We plug in what we have. How nice, they're the same. 0.0515 molar hydroxide. Initially, these products are 0. Do you recognize this? We are at the equivalence point, EQ point. At the equivalence point, we have equal moles of acid and base according to the ratio in the balanced equation, which is 1 to 1. This is perfect. We're at the equivalence point. Now, this was wonderful in the strong acid, strong base titration. We reacted the original hydrogen and hydroxide as completely as possible. All we formed was water, and it was a no-brainer. The final pH was 7. Unfortunately, this one's going to suck a little bit. We're going to react these as completely as possible, so we will bring these reactants down to 0. That'll be 0. 515 down to 0. These are going to go up. 15. So this will be 0.0515. And we're going to form some water. 0.0515 moles of water. Okay, so between the two products, last time all we had was water. So pH was just 7. This time we have water, but we also have some of this acetate ion, which is weakly basic. So between these two, the acetate or the water, the one that's going to have a greater effect on the pH, not the water, it's that acetate ion. So this sucks. There is no way around it. We got to do another ice table. Oh, I forgot to erase some of my last ice table. Unfortunately, we need to find the pH now of this weak base solution. All right, so here we go. We've got the acetate ion, CH3COO minus. This thing has a tendency to go backwards. He's attracted to hydrogen. Where's he going to get it? From the water. So we'll be left with the acetic acid molecule and hydroxide. Ah, fun. Okay, so this is just going to be like a typical weak base problem, like just what we had done in the last chapter. It could have been like sodium acetate. We want to find the pH of the solution or something like that. So we'll do an ice table. We've got the original molarity. We don't care about the water, so we could essentially get rid of it. And then these products will be 0. We don't have any of those remaining from the original ice table. All of the acetic acid in the original ice table has gone forward. But we know that this acetate ion, being a weak base, will have the tendency to remove hydrogen from the water molecule. All right, so this has to go forward. We just don't know by how much. So we'll call it X. 1, 5 minus X. We're not going to care about the water. These are going to go up by X. Up by X. So they will just be X and X. Excellent. So I want to find X, and then I can find the pH of the solution. To solve for X, originally they had given us the Ka of acetic acid. But now we've got the conjugate base. So remember, you have to change that to the Kb. So we'll do Ka times Kb equals Kw. The original Ka was 1.8 times 10 to the negative 5th. We're looking for Kb because we've got the base ion. And that should equal Kw, 10 to the negative 14th. So it's not hard, but it's something that we can't forget to do. We're using the base ion of that original weak acid. So I got my Kb. Oh, let's go 5.56 times 10 to the negative 10th. Ooh, that's small. That's going to equal X squared over 0.0515 minus X. And there is no doubt in my mind that we can 5% rule this thing. That K value is super, super small. All right, so we'll cross multiply. We'll take the square root and solve this thing for X. How about, ooh, tiny X. 5.30 times 10 to the negative 6th. Wow, that is small. Of the 2 particles produced, we're going to have some acetic acid. The acetic acid is a weak acid. We're also going to form some hydroxide, which is the sign of a strong base. So of these 2 particles, the one that I'm more concerned with, the one that's going to affect the pH more, is the hydroxide. So let's do this. POH might be the easiest route. That's an H. Opposite log of the hydroxide, the 5.30 times 10 to the negative 6th. So plug that in. 5.28. And then we can just subtract that from 14 to get the pH. The pH is about 8.72 maybe. And then we ask ourselves, does this kind of make sense? Actually, it does. If we look back at that original graph, we kind of estimated that, you know, the pH at the equivalence point, like halfway kind of in that big jump, should still be slightly basic. We've got a strong base and a weak acid. So even though we're at the stoichiometric ratio, the final solution should still be slightly basic. So this does make sense. I'm expecting a pH greater than 7. So like 8.72, that seems reasonable. Here's the last little calculation with this strong base, weak acid titration. I promise this one's better than the last one. Okay, first order of business, redo the molarities. Do it first so that you don't forget. Otherwise, I know I forget. 0.1. And it's easy, so you might as well just do it right away. And then you can set up your ice table and go with it. Initially 25 milliliters. We want to know the new molarity when the final volume is, let's see, 55 milliliters. All right, M2. 0.0455 molar. The base was 0.1063 molar. Originally, we've got 30 milliliters. M2 is what I want to solve for at a final volume of 55 milliliters. Oh, let's see, 0.0580. That looks good enough. So again, they're the same molarities as the strong acid, strong base titration, but our ice table looks a little bit different. Let's set it up. Weak acid, COOH, plus the hydroxide from the strong base. La la la. We're going to rip off a hydrogen, so we'll be left with the acetate ion and water. Okay, so let's see what we got. Ice table. We'll plug in our new molarities. Since we joined volumes, they'll change just a little bit. 0.455, 0.0580. And initially, no products. Here's kind of the limiting reactant portion of a titration calculation. We want to react these as completely as possible. So we're looking for whatever one's smaller. It's the weak acid. So let's bring this down to 0. And then we react everybody else accordingly. This is going down by 0.0455. So we'll be looking at about 0.0125. These guys are both going up. So at equilibrium, we're 0.0455 molar. Eventually, there we go. And we will form some water. 0.0455 moles of water per liter of solution. Okay, so we assess the situation. What do we have left? We have some hydroxide. Hydroxide is the sign of a strong base. We have some acetate ions. Ooh, that's fun. Acetate ions are the sign of a weakly basic. Oopsie. That's supposed to be a W. Weakly basic solution. And we've got some water, which if I'm deciding between these three particles, I really don't care about the water. That's not going to affect the pH. So between the hydroxide and the acetate ion, I'm pretty confident that the final solution is going to be a base. Do I somehow have to use both of these ions to calculate the pH? Heck no. Between these two, let's get rid of that. Oh, I shouldn't say get rid of it. We can kind of ignore the acetate ion. Yes, the acetate ion is going to react with some hydrogen from the water, but that's going to have lesser effect on the pH than this remaining hydroxide that's just floating around in the water. We are totally safe taking the pH of this final solution solely based on the extra hydroxide. See, I told you this one's not so bad. So we can really just go, let's do POH right away. Opposite log. 0.0125 molar hydroxide. That should get me about 1.9-ish. And if I subtract that from 14, I get a pH of about 12.1, which seemed pretty accurate if we look back at the original graph. We've gone beyond the equivalence point now, so I should have excess base. In any situation, if you're trying to calculate pH and you've got something strong and something weak, you can always base your pH on the strong ion, the hydroxide or the hydrogen. If you really wanted to, you could take this reaction and flip it backwards and do another ice table and figure out, well, how much extra hydroxide is formed when this acetate ion removes hydrogen from water. The final amount is insignificant. It won't have a substantial effect on your final pH. So you really can just base the pH on the concentration of a hydrogen or hydroxide ion that might be in excess. There, I promise that last one wasn't as bad as the first one.